Hello, this is Sukantade from IIT Guwahati. My topic is Design Methodology for On-Chip Power Grid Interconnect and AI/ML Perspective. So as we know, the modern VLSI chips are chip design becoming increasing due to the increase in the number of transistors. So the initial phase of the chip design is an RTL synthesis. So after the RTL synthesis, we need to make the physical design of the chip. So the three major important steps is floor planning, placement and routing. So in the floor planning stage, power grid interconnects are designed. So this process power grid design phase is also known as power planning stage, where two major issues need to be dealt with: IR drop and electromigration, in order to ensure the reliability of the chip. So what is IR drop? When current passes through an metal interconnect, some voltage drop occur due to the resistance of the metal line, and this voltage drop is known as IR drop. And the objective is to have a less value of IR drop as possible. And what is electromigration? The electromigration um, means when current flows through a metal interconnect, there is a transfer of momentum from the from the electrons to the metal atom, and due to that some metal displacement occur, that is known as electromigration. These two issues need to be held in this power planning stage in order to increase the aging of the chip, in in order to increase the lifetime of the chip or the reliability of the chip. So this is a toy model of its associated with power grid connections. So this is the power grid which is connected to the underlying functional blocks, and this is a power pad. So in order to explore the power grid, we need to formalize it, and we do a electrical modeling like that. And here in this work, in our work, we have used steady state models. So only we have taken the resistive elements, and for the functional blocks we have modeled these as current sources. And now what are the power grid design challenges? So one is the large size of the power grid due to the increase in complexity of the chip design, and again IR drop and electromigration need to be checked. And another is it is difficult to find the optimal design point. So another is existing method are semi automated and manual. It takes huge amount of time and also human power. So there is a need to explore for better design methodology, and we believe AIML approach can be a good alternative. And in order to in the same direction, we have proposed some of the works. My work is basically divided in four parts. Firstly, we have proposed a fast probabilistic power grid analysis method, and secondly I have tried to find the optimal design point using meta heuristics. The first two approaches are not purely ML based, but it comes under the purview of artificial intelligence. ML based power grid, and my third work and fourth work is purely ML based. The third one is ML based power grid design, and fourth one is ML based aging prediction. So in the first work, we try to find the power grid analysis, or in other words, the voltage of the power grid nodes. So for that, we converted our power grid network into an annotated graph, and we have adopted a random walk based approach, which is a well-known approach in the literature. The demerit of the random walk approach is it uses self loop to find the voltages, and due to that it consumes lots of time in that self loop. We try to remove the self loop, and we adapted a jumping way strategy called Levy flight to speed up the work, and we validated our approach in different test cases, and we have say that for highest 49 million nodes we have got good speed up. So we achieve a maximum speed of 60x over the random walk with an accuracy of 4%. So with this work we basically try finding the voltage node voltages of each of the points. In other words, we are trying to find the IR drops of the power grid network. Then our second work is in our preliminary work we observed that IR drop minimization can, can be done with the increase in the metal area. And again we have another experiment. We have found that if we decrease the metal area, the airdrop increases. So this airdrop and metal area both are conflicting objective. So in order to find an optimal design point, we formulated this as a multi-objective optimization problem, and we solve it using a heuristics. So for that we take a large power grid network and we divide it in sub circuits. For each of the sub circuit we used this meta heuristics. These heuristics we used a NSGA2. This is called non-dominated sorting genetic algorithm. So we use this meta heuristic for each of the sub circuits, and we try to find the optimal Pareto fronts from. And if the from the optimal Pareto we have taken a optimum solution, and then if the optimal solution is found for each all the sub circuits, and we call that as sino, we call that we have achieved the optimum point. And in our experiments we have got around 7% reduction in the worst case airdrop and 8% reduction in the metal routing area. And this work is published in Elsevier Micro 2021. So after that we have used ML based power grid design. So in this work we have created a dataset, and for creating the datasets we have used IBM power grid benchmarks which are available online. So from that, what feature we have used, so for a single metal line connected to a current sources at XY location, then the input features are XY location, and the ID value of the current is taken as the input feature, and the output feature is the width of the metal line, and these are taken for all the metal interconnects. And using this we created a training data set, and then we trained a neural network. And for a similar kind of unknown data set, we created a test data set and we trained the model, and we got a predicted power grid design. So from this power grid design using Kirchhoff's law, we have found the airdrop map, and this work was published in date 2020. And so here this is the airdrop map using the conventional approach, and this is our proposed ML approach, and we got same quality of results using ML, and our error is 22%, and maximum speed we have got as 5 to 6%. So this is ML based power grid design methodology. So once we get the design, it is required to find the lifetime of the power grid during the design phase. So some physics based models are there to find the lifetime of the power grid interconnect, but those are very time consuming lifetime. So we have adapted a ML based approach, and similarly we take supervised learning approach, where our features are: J is current density, L is the interconnect, T is the temperature, airdrop is the airdrop, and these are taken as the input feature, and MTT was taken as the output feature. So using this we created the trained data and trained a neural network. Again for another part of data set, we created a test data set, and we then tested our model, and we have got some MTTF value. And here we have applied a failure we have proposed a new failure criteria in order to match the so you can see this result in this paper. This is published work. And after that, in order to find the mortal interconnects, we have another ML model is created, logistic regression based ML model is created, and we compared our results with the state of the arts. And here you can see that our proposed ML approach achieve speed up of 778x over this and 278x over this, and 276x over this 10 ticket 2018 work. And so basically we have got a speed up over all the state of the art works. And accuracy wise, our ML approach is closest to the accurate method of TK 2016 and better than all other state of the art methods. So this is our work on ML based aging prediction, and this is my publication, and that's all about my interview. Thank you.